Okay, let's have a look at a momentum example. In a rear-end collision on a freeway, a car of mass 1 times 10 to the power of 3 kilograms travelling east at 20 meters per second crashes into the back of a bus of mass 5 times 10 to the power of 3 kilograms travelling east at 8 meters per second. Answer the following questions assuming the car and bus lock together on impact and ignore friction. Okay, so the key to this is knowing one simple thing, that I'll do it in red. The momentum initial, so momentum before, will be equal to the final momentum. Okay, the momentum before the collision is going to be equal to the momentum after the collision. That's important. Now that's the total momentum, looking at everything in there. So, in order to work anything out, we need to work out our different momenta. Okay. So let's work out the momentum of the car. Okay, so our momentum of the car before the collision. Our car, so it's mass times velocity. Our car has a mass of 1,000, which is just 1 times 10 to the power of 3. There's our mass. Our velocity is 20 meters per second. So our car's momentum initially is 20,000 kilogram meters per second. Okay, there's our car's momentum. Our bus's initial momentum. Now, it may help you to draw a diagram with this sort of thing because our car and our bus are both traveling in the same direction. Okay, so we can have everything as positive. If one is going in a different direction, you might need to have a negative as your momentum. Okay, remember in problems like this, negative is just the direction you're heading in. So let's do our bus's momentum. So the mass of the bus is 5,000. And it's travelling at 8 meters per second. And so that will be 40,000 kilogram meters per second. So our initial momentum, prior to the collision, we need to look at everything involved in the collision and take the momentums of those. So our initial momentum is going to be the momentum of the car plus the momentum of the bus, all before the collision. Okay, so it's 20,000 plus 40,000, so we have 60,000 kilogram meters per second. So that's our initial momentum. We know from up here that our initial momentum and our final momentum are exactly the same. Okay, momentum is conserved. Whatever you have at the start, you're going to have at the end. So that means our final momentum must also be 60,000 kilogram meters per second. So we've got our final momentum. We want the final common velocity of the vehicles. Now if we have a look, answer the following questions assuming the car and bus lock together on impact. So if they've locked together after the impact, you can consider them as one object. If they're locked together, they're going to be travelling at the same speed, right? So, from our formula again, our momentum is equal to mass times velocity. Now, if we're looking at our final momentum, we know that 60,000 is going to be equal to the mass times the velocity of the car and the bus joined together. So what's our mass going to be afterwards? 6,000. Our car and our bus have become joined together. So the mass of the car-bus combo is 6,000. All right. 6,000 V. Sorry? It's nice, isn't it? It just seems to work out beautifully. Okay, so we have a momentum, we have a mass, we can rearrange this, and we get V is going to be equal to 60,000 divided by 6,000, which is going to be 10 meters per second. Okay, so our car and our bus. So our car was traveling at 20 meters per second, our bus was traveling at 8. They collide. It sort of makes sense that the velocity of them both afterwards would be between those two. Okay, which is what we've got, 10. If you have a car travelling at 20 and a bus travelling at 8 and the final speed is 40, that seems unlikely. So you may need to check what you've done wrong there. Okay. So that's how you do one of these problems. You assume, well, it tells us here that they lock together. So when it locks together, you can assume that the mass can be taken as one quantity. The important thing is whatever you have for momentum at the start, you're going to have the same thing for the momentum at the end. Okay, calculate the change in momentum of the car. Anyone remember that nice physics word for change of momentum? Impulse. Impulse. Very nice. Change of momentum is impulse. Okay. So to work out the change of momentum in the car, well, our change in momentum is going to be equal to our final momentum minus our initial momentum. That's all change is. What you get at the end compared to what you get at the start. So, yes. The momentum of the whole system doesn't change, but the momentum of the car does. If you just look at the car, the momentum of the car changes, but the whole system, the car and the bus together, that doesn't change. Okay, our momentum of our car. So if we're just looking at the car, now we need to take the car's mass as separate from the bus if we're just looking at the car. So the final momentum of the car, our car weighs 1,000 and it is travelling at 10 meters per second after the collision. Our initial momentum, we worked out up here, was 20,000. So 10 times 1,000 is 10,000, even I can do that, minus 20,000 give us negative 10,000 kilogram meters per second. What does negative momentum mean? Opposite direction to the way you were heading. So remember, momentum is a vector, it has a direction. So originally our car was heading east, so its change in momentum is going to be 10,000 kilogram meters per second west. Okay, it's lost momentum. You could. Yeah, you should. Let's do it. Okay, so there's our change in momentum. Oh, yeah, good point. If you've got the direction, you don't need the negative. Yeah, fair point. Okay, so here we have a calculation of final momentum and a change in momentum. What's next? Change in momentum of the bus. This should be nice and easy. So our momentum, our change in momentum, is going to be equal to our final minus our initial. So, our final momentum of our bus, now it was 5,000 kilograms, I think. 5,000 kilograms multiplied by its final velocity was 10 meters per second. So that's going to be its final momentum. Minus its initial momentum, which was 40,000, wasn't it? 60. Oops, sorry. Was it just the bus? It was 40, yeah, righto. Just the bus. Just the bus. Okay, which means we have 50,000 minus 40,000, which is 10,000. Now that's positive, so it is in the same direction as it was travelling. It's east. Now this all makes sense. Our car has slowed down. It's gone from 20 meters per second to 10, so it's had a reduction in its momentum. That's why we get that minus. The bus, on the other hand, has sped up. It's gone from 8 meters per second to 10, so we get an increase in momentum. Okay, verify that the momentum of the system is constant. So we need to verify that our initial momentum is going to be equal to our final momentum. So our initial momentum is made up of the momentum of the car plus the momentum of the bus. Which is equal to Our final momentum, let's look at the final momentum of the car. Oh, well, we could do this in a couple of ways. Okay, so our final momentum of our car was what? I can't go back. No, hang on, that was a change in momentum. 60,000? Hang on. The whole thing. So hang on, the car, trying to remember without going backwards here. The car was 10 meters per second at 1,000, so it's 10,000 was the final velocity of the car. No?
Oh, yeah. 10,000.
Yeah, oh, sorry, the final momentum of the car is 10,000. Now, I've confused myself now. All right, here's the easy way to do this. Okay, let's look at, hang on, we'll do the other bit in a second. The change in momentum of the car, actually the change in momentum of our system. Equals the change in momentum of the bus plus the change in momentum of the car. Okay? So if we look at the change of momentum in the entire system, that's made up of the change of momentum of the bus and the change of momentum in the car. We add those together to find the total change. The change of momentum of our bus, we've got right there, 10,000. Change in momentum of the car was what? Negative 10,000. 10,000 plus negative 10,000 is what? 0. We have no overall change of momentum. Okay? This is verifying that the momentum of the system is constant. Okay? Now, what I was working on down here, our initial momentum we worked out before, the total initial momentum was 60,000, right? Our final momentums. So I can see here, our bus's final momentum is 5,000 times 10, so it's 50,000. Plus, our car's final momentum, yeah, I'm sure that was 1,000 times 10 on the previous slide, is 10,000. And so you can see our initial momentum of 60,000 is equal to the final momentum of the bus plus the final momentum of the car. So you can work it out either way. Look at the change in momentum that's happened, or compare the initial momentum to the final momentum. And you should see they come out equal, and you find there is no change in momentum.